we're sort of down to the wire. I can write the rest of the semester on the board. This is all on WebAssign, of course, but, oh, yes. Oh, here. Some things, though, that are important coming up, and just to ensure that it's on your radar, lest you forgot, the superhero paper peer review is due this Friday. That's the last minute. Since the beginning of the semester, you had until Friday, although only one person has completed the assignment, but that's typical. Everybody waits till the end. On that, though, before we leave that one, how many of you are having a difficult time getting somebody else in the class to review your paper? How many have I even asked anybody? It's due Friday. Tell you what, take 2 minutes. Find someone. Exchange emails or something. This is what's typically done. Because you probably haven't printed it off or anything. You know, email them a copy. They can read it and answer the questions on WebAssign for it. It's not difficult. By you reading someone else's, you get to see what they did and like, oh, I didn't think about that. Oh, that's a good idea. Oh, I didn't like that, so I'm going to improve all that stuff in mine. Likewise, they give you that feedback so you can make the paper better. So take a minute or two here and figure out, if you haven't, who's going to review. Yes? Can we have like a three-way kind of thing? Yes, it could be like this. Will you review mine? Great. And I could review his. Or he could review his. But hopefully, you're having yours reviewed, and you're at least reviewing someone else's. It does not have to be someone in the class. It's just, it would help you more if it is. So take a minute, go.
When I took it the last time, and we were doing like things like frequencies and overtones stuff.
Oh, you did. I forgot you did that.
I was like, just remember that we did certain waves. I'm like, I can't remember. Like, I didn't know if he still did it. And the curriculum was like, I can't remember. I wonder if he remembers me doing that.
Oh, I remember having students do it. I forgot it was you. Were you successful?
With music?
Yeah, singing in the thing.
Oh yeah.
The wine glass.
I think we did it. Oh, I don't know if we did the wine glass. I sang in your computer, I think.
Oh, it was the. Oh, that's probably why I didn't remember. I've had somebody try to sing into a glass and it broke. But that's harder.
It's actually relatively easy. All you have to do is find.
Well, if my computer gets back, I can do that to show the waveforms.
Right. You can see the overtones.
Yeah, it's a lot clearer. Did that help? So, you read your person's paper. The questions you're supposed to answer are your WebAssign assignment. I say in there, it's the same questions and comments that follow the rubric, how I'm going to grade it. So that you can match right up and see the points and not overlook something. Now, I am taking you on the honor system. If I catch you trying to cheat at this, you get a 0 for the whole assignment. But the idea is you share your comments with the person you're reviewing. In other words, it's possible that I could read your paper, enter all my comments, I could even make them up, but that's cheating. The idea is you then print this or a screenshot or something and email it or bring it into class and share it. Otherwise, it doesn't do that person any good. I can ask that other person that you claim, because I ask, who are you reviewing? Who reviewed yours? And if it doesn't match up, you didn't do it. So share that info. But yes, Friday is the last day for that. Likewise, then, you'll have a week to revisionize it. Is that a word? And turn it in the following Friday. Not this Friday, but next Friday. That's the deadline. You can turn it in before that. Please reread the grading. in the rubric so you don't miss something. Especially with the final submission, I ask you to turn it in. You'll upload it in WebAssign. But I also want to print it hard copy. Friday. That's the deadline. Questions about the paper?
So the deadline is before class on Friday?
Well, if you can catch me before I leave Friday, you could come after class, but I'm not going to be here all day. In other words, if you're like, oh, I didn't see that, I forgot, and you hand me the paper Monday, that part's late. You've had all semester to do this, so. Okay. We're starting our last unit, and that'll be exam 4 with the date there. And then the final exam that's been posted, I didn't set that, the university did. It's on WebAssign. But please note, it's on the 13th of December. It starts at 10:30. It's not the same time as our class. It overlaps, but it starts at 10:30. It is right here, though. You don't have to go anywhere different. That's listed in the syllabus and on the calendar. No. Some people will take the whole 2 hours. The final will be comprehensive, as stated in the syllabus. Say again? It'll be 60 questions over all semesters' material. I spread it out pretty evenly. Roughly a quarter from each of the units, the 4 units we've had. It's the same format and style, though. It's multiple choice. There'll just be 60 of them. So for those, there's not an opportunity for a retake on the final since classes will have been over about a week by then. I don't intend to curve any of my tests until I grade them and see if, the majority missed this question, or so I must have had a problem, or something was bad, then I change things. But so my intent is not to curve it. I'm not against curving it, but I wait to see how it turns out. Yes?
How many of those chapters will we get through before exam 4?
All.
All of them?
Is the final included in the test that you drop at the end of the semester, or is that just the 4?
Yes, I mean, the short, no, but yes, I see where you're going. You all have had 4 exams, midterms, you will. I'll drop your lowest score of those. No, if your final is the lowest, oops. Yeah, so you could have bombed all the others, but yeah, I want to see, all right, what's the takeaway? What are you leaving this course with? So that is, I believe it was 20% of your overall grade. Yes?
Do you have a review or anything?
Yes, after the way it worked out, exam 4 is on a Friday, and we'll have 2 lectures after that. Usually I only have 1. So we will have 2 lectures the last week of classes to review any and everything. I mean, can't go into grimy detail, but it'll be good to, oh yeah, bring your questions. Look over the past material, see where you got stuck. That's the great stuff to do. By the way, I look back, and still only about 1/3 to 40% of the class even bothered to go back and look at the answer keys. There was a comment, question?
Just will there be a cheat sheet allowed?
Yeah, same format. You can still use a cheat sheet for the final in the calculator. Same style. I'm not changing things up, just a little longer to include everything.
Those are still available, right?
What?
For the exams, those answer keys are still available, right?
Yeah, everything's still available on WebAssign. Have been as soon as they're due, you could access them back again. It's just you go under, you only see the current assignments by default. Just click on past assignments, and I've always been there. Okay. So yes, this does look like a lot. My quick answer is they're very similar. We're going to start this. I call this the waves unit. We're going to start with vibrations and waves and sound and then move into light. Well, light can act like a wave. And so many of the properties we're going to introduce here are the same here. So these will actually go a lot quicker. We still roughly get 2 lectures on each chapter. I think one of them's shorter. We don't need it all, but it's all laid out in the calendar. But it's all things that vibrate and wave. I will admit the last 2, we don't go into as much depth as the textbook does. And I can remind you of that when we get there, but you won't remember by now. So let's start chapter 19 with vibrations and waves. As your book states, a vibration is a periodic wiggle in time. So I'm vibrating. I'm wiggling with time. As time changes, I'm wiggle. This is wiggling back and forth. You go up and down, up and down. I'm not really going anywhere. My net displacement, I'm not moving anywhere. Yes, I'm moving. I'm vibrating. I'm wiggling, but just with time. So this is wiggling with time. This is wiggling with time. It's vibrating back and forth, back and forth. That's a vibration. The source of all waves is a vibration. Something has to be vibrating, changing with time, wiggling. That's the core behind everything. To create these waves, well, then we'll look at the properties of the waves and how they can interact and whatnot. But remember always, that's the source. Something has to be wiggling. So like this. What was it? It's me doing work on it. I made it vibrate. I pushed on it. Or this, my internal forces. So how is that different than a wave? A wave is a periodic wiggle in time and space. We talked about space-time. You got change in position, change with time. So see, this just moves back and forth. That's just a vibration. To create a wave, it has to displace through space. So I could do this. I could make it wiggle back and forth and then move with it. Now the tip of that pen is kind of like moving through space. It's not just moving back and forth with time, it's moving with, do you follow that? I came up with this, I gotta admit, I'm proud of it, I like it, to help you visualize this. This is an ultraviolet laser pointer. So it emits a purple light that we see, but it mostly emits ultraviolet light. And then I have, oh, silly me, left the screen in here. This is a glow-in-the-dark screen that fluoresces when the UV light hits it. So I'm going to dim the lights. Let's try that one. So you can see what's going on. I will vibrate this. It's missing the mirror, but it'll settle down. You can see it vibrating, wiggling it with time. So here I am. I'll hold this. Let's see. Right. There, you see it wiggling up and down? That's a vibration. Now let's create a wave by translating it through space. So now not only does it move up and down, it goes back and forth. Let's go a little darker. There it is. So vibration. Now, it creates a wave. If you go, oh, well, thank you. If I go faster through space, the velocity changes, and the wave looks different. Or you can go more slowly, of course, too. Let's see. You get the idea. The source of all waves is something vibrating. So it wiggles with time and space. Make sure we get that down since everything else we're doing is based on that. Let go. Now, we're going to start with sound. We'll get more about it, but I can't help but kind of talk about 20 as we go along. Sound is a mechanical wave. The propagation of the vibrations have to go through something. Sound needs a medium. Oh, the waves need a medium. They got to travel through something because they make the something vibrate and wiggle, and that's how it propagates through space. Example, this. Call it a wave machine. If I make it vibrate, you can see the wave travel through space. But just focus on an individual rod, maybe this one. Watch what it does. It goes up, down, up, down. See, it just wiggles. But it doesn't. So that's a vibration. It vibrates. The wave is what's getting translated and propagated. It's going through the rods. It needs this rod, which are connected by a wire. Oops. And that's how the vibrations are translated to its neighbor. When we get to light, that doesn't need a medium. It's still a wave, but it can do it all on its own. It's like pure energy. It can travel through a vacuum, through empty space. It waves all on its own, kind of self-propagates, if you will. Something still has to create the wave. The source of all waves is a vibration. Something has to be vibrating. It ends up being a charge. Charges that vibrate can create light. Here, you got to make something physically vibrate, and then it needs that physical medium to go through. You guys have heard of electromagnetic waves, I bet. The electromagnetic spectrum. We'll cover that more when we get to light. What are some examples or types of electromagnetic waves? Light, good. Visible light. What else? Microwaves, gamma rays, X-rays, radio waves, infrared, ultraviolet. Those are all forms of light. It's just only a small portion is actually visible by our eye. They all are a wave. They all don't need a medium. So what's different about them? Their wavelength is one way to think of it. You've probably heard of terms before: wavelength, frequency, period, energy. Those can change. That's what's different. So let's discuss a bit what those are. That's what we'll get to today. Let's start with the period, what a period is. If we look at a pendulum, this is a simple pendulum, a mass on a string. It vibrates back and forth. Whee! How long it takes is called the period. The period of time it needs. So we use a T, but we make it a big T. That's the period. And so its units are time, seconds. How long does it take to make one complete vibration? So it's like this. If you start here at this side, you watching? 1001, 1002. It took 2 seconds to complete one cycle, to get back to where it started, to go through one vibration. 1001, 1002. That's the period. Yes, period is time. So it's the time to complete 1 vibration. Whoop. Or cycle, or revolution, or repetition. So, you know, something's going in a circle. 1001, 1002. 1001, 1002. Things that go around are repeating. They're vibrating. It's a wiggle. They're not making a wave because they're not translating through space. But that's the period. Cars, wheels, 1 RPM, revolutions per minute. That's a period. Now, that's the rate. Revolutions per minute. How long does just 1 revolution take? Is the period. Well, let's do that. Let's say you have 60 RPMs, revolutions per minute. You can go around 60 times, 60 cycles, revolutions is what it is, in 1 minute. What would the period be? Yeah, you could think of that as 60 revolutions per 60 seconds, because that's how long 1 minute is. So yeah, it's 1 revolution in 1 second. So yes, it goes around once a second. So the period is 1 second for that example. Does anybody know what we call this? What's that? Frequency, very good. That's another term then. Frequency. Initially, we'll have all this vocabulary so that we can describe these waves, because we all have to be on the same wavelength. Okay. Frequency. It's F, and it is the inverse of the period. You could have looked at this one and said, the period is, it does 1 revolution, no. 1 minute in 60 seconds. Come on, Adam. 1 minute, 60 revolutions. You flip that over, the inverse of it. So it's 1/60th of a minute. That would be the period. You know, we did it in seconds because that was easier to see. If it does 60 revolutions in 1 minute, then in a 60th of a minute, it went around once. You see, that's 1 second. I hope. Did you follow that? Be honest. Because it sounded kind of fuzzled in my brain. So you were with me? No. So if you do if you go around 60 times in 1 minute, then to just go around once, it was a 60th. Hence the inverse relationship. That's what I'm trying to emphasize. We'll do another example. This, then, the units are inverse seconds, 1/2. And that's common. It has a name, Hertz, H-Z, after a scientist's last name. So now we can do an example. If you had something that's 60 hertz, for example, our electricity, the alternating current, the AC current, changes direction. That electric field changes directions at 60 hertz. That's the rate at which it's vibrating. That's what frequency is, the rate. So that's the same as like 60 inverse seconds. What would the period be then? Right. It's just the inverse. If that's the frequency, then the period is 1/f, 1/60 hertz, which is a 60th of a second. 60 hertz means it is going back and forth 60 times in 1 second. Just like this one, 60 revolutions in 1 minute. This one is 60 revolutions in 1 second. So it's going back and forth, changing directions. This way, this way, this way, this way, this way. 60 times in a second. That's the frequency, the rate. Thus, in a 60th of a second, that's how long it takes to go back and forth just once. That's the period. So the current in our wall system in the United States is changing directions every 60th of a second. What's somebody's favorite radio station? 90.1. Now, scientists don't like answers just like that. 90.1 what? Do you know? Very good, Dave. Megahertz. It's a frequency. Your numbers on your radio stations is the frequency at which that radio station broadcasts its electromagnetic wave, its radio wave. It is vibrating at 90.1 million times every second. That's its frequency. What would the period be? 1 over 90 million. So it doesn't take long at all for it to go back, vibrate just once. So remember this relationship. You got the definitions, the concept of what period and frequency are? Let's test you. Okay, you ready? 1001, 1002. What's the frequency? One-half hertz. A half a hertz. It does a half a vibration in a second. It makes it over to here in 1 second. That's half of it, right? There you go. All right, let's look at these pendulum more closely. These have the same length, but this one's a lighter rubber ball, and this is a heavier steel ball. So they have different masses. I'm going to displace both. How do you think their periods and or their frequencies will compare? The lighter one should go faster? Heavier one will go faster. Well, we're split, aren't we? All right. Ah, it'll switch back and forth. Who thinks it'll explode? Okay. Yeah, it's a trick. As soon as I let go, that'd be cool. I got to figure out how to do that. That'd be nice. Okay. All right, here goes. The same. So we just learned something. The period, the only difference there is the mass, right? So it's not proportional to mass. It doesn't care.
If the string was a different length,
Well, let's try that then. Which one do you think will vibrate faster? Now we have to be careful when we say that. Vibrate faster. Am I talking about the frequency or the period? It can be confusing. So I'll try to be more clear, and if I slip, you call me on it. Which one will have the higher frequency? In other words, go back and forth more quickly. The shorter? Yeah. And now you have more of a consensus here. Let's see. Well, okay, less amplitude so they don't hit each other. Oh yeah, can you see this one going back and forth several times in the time it takes this one to? So yes, this one has a greater frequency. It's vibrating more quickly. How do the periods compare? Yeah, this has a shorter period because it goes back and forth more quickly. So the time it takes is less. This one takes longer, so the period would be bigger for this one. So the one that takes longer, bigger period, T is bigger. Takes more time. All right. So the period is then proportional to length. Let's see. What do you think would happen if we took this experiment to Jupiter or the moon? Would anything change? There's no atmosphere, so we all die. But let's say, get out of the spaceship, go like this, hop back in. What will happen? Okay, we know gravity's different. What's making these swing? The source of, what's the source of this vibration? Yeah, when I let go of it, who pulls on it? Gravity. That's what accelerates it down. But then the string says, no, wait, go this way. And so gravity's always pulling this down. It's driving it, so to speak. So if we change gravity, do you think it would go slower or faster if we went to the moon where there's less gravity? We'll go with that. Slower. It would vibrate more slowly because the gravity would be pulling on it less, trying to accelerate it less. Look at this example. Gravity. That's how fast it takes. Here, let's go from this height. This is how fast it takes to go down quickly. That'd be a short period, right? We could bounce it. Doink, doink, doink. One revolution. Well, what if we slow it down, go down an incline? Now its acceleration is less than g, right? And it takes a lot longer to get to the bottom. With the slower acceleration, the slower g, it takes longer. So for a bigger t, you get, with less g, you get a bigger t. So those are proportional, but inversely. As you decrease gravity, like going to the moon, it takes longer for it to go back and forth. Jupiter, that has more gravity, yeah, g would be bigger. Period would be smaller, which means it's going back and forth more quickly. Doesn't take as long to complete. Right. Well, if you put all this together, there's a formula to guide our thinking, and it works out to be looks a little scarier. It's not a linear relationship. It's actually by the square root and this 2 pi. Because it's kind of, you can relate it to going in a circle, repeating itself. The concept I'd like you to note is, see, if you make it a longer pendulum, that's the length of this pendulum, then the period will increase. It'll take longer to swing. If you go to Jupiter, where gravity's pulling on it more, harder, it'll make it smaller and it'll vibrate more quickly. But again, notice mass is not in here anywhere. So you can hop in your playground swing and then let little Timmy get in it. You should swing at the same rate. Because you're both on Earth and the swing is the same length. And you can try it out.
Sorry, you said if the length increases, then the T decreases.
No. It's directly proportional. If this gets bigger, that gets bigger. If that gets bigger, that gets bigger. Right, that's an inverse relationship. G increases, that means T is getting smaller. Frequency would just be all of this flipped. because frequency is 1 over this. So, it's a simple relationship between period and frequency, but I tend to not be able to emphasize it enough. People get confused. Just think clearly what you're trying to discuss. You want the time, or do you want the rate? The period or the frequency? Because they're inversely related. The faster it vibrates, the shorter the period, but the bigger the frequency, and vice versa. So just trying to make it clear so as you go through all this, it won't be as confusing. Sound clear right now? Got it in your notes? Okay, good. More definitions then. So we got a vibration in time, went up and down, but as it moved through space, we got a wave, and it looked like this. It's called a sine wave, and it can be defined by the trigonometric function sine. Just know it's a sine wave. We call this spot in the middle the equilibrium position. That's where it likes to be. So like with this pendulum idea, this is the equilibrium position. This is where it wants to be. If I displace it away from it, that's like going up, let's say. But then it comes back to the equilibrium position, crosses through it, and goes the other way. It keeps crossing it. So does a sine wave. Cross, 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 cross. It works that way with a mass on a spring, too. Let's do that one. Hang that there. We'll grab a mass. We'd call this the equilibrium position. It's happy there. But if I displace it, I just went, say, down on the curve. Up, down, up, down. But you see it cross the equilibrium position. We call how far it goes the amplitude. How far you displace it away from the equilibrium position. This is all in your book, too. Now, it's going to go the same on the other side. So these amplitudes are the same, just in the opposite direction. You can see that. This swings the same amount on one side as it does on the other. That would be the amplitude. Or this is the amplitude. Over here. That's the amplitude. See if I can. I messed up. You get the idea? All right. I like to call these the crests, and these the troughs. That's typical. They're the bumps, the up bump and the down bump, if you want. I'll know what you mean, but the one that goes up is positive direction, crests, and down, troughs, because they look like troughs and crests. All right, if we go from, say, this point to this point, we're back to where we started in time, so to speak. So you start up here, displaced yay far away from the equilibrium. You cross the equilibrium, you get displaced on the opposite side. You come back, you cross, and you end up back where you started. So we represent this wave, this vibration with that wave. We start here, down, back, and there we are again. That's one complete cycle. How long does it take? 2 seconds, and we call that the period. Yeah, so the time it takes to go from there to there. The time is the period. And we give, since the wave not only vibrates in time, hence the period, it also goes in space. So the distance it covers is called a wavelength. So the actual distance is a wavelength. Most people represent it with the Greek letter lambda. But often, because we can't do that digitally through things, a W is fine. I'll accept either. So that's the wavelength. Likewise, can you see that from this spot to this spot? It's just from starting at the other side. How long does that take? Same period, same wavelength, too. That's the same wavelength. Heck, you could start anywhere. Let's start here at the equilibrium. Swing one way. We're back to the equilibrium, but we're coming in the wrong direction. So you go back. Oh, now we're back to where we started in the same direction. And again, that'll take one period and B and travel one wavelength through space. So now you guys get to remember back to your forces in motion and the kinematic equations and things. We learned that velocity, how is it related to distance and time? What is velocity? Distance over time. It was a change in our position with time. It was the rate at which we were moving through space. Well, waves have a certain velocity. They go a certain distance in a certain time. We now have terms for these. The distance is what? A wavelength. And the time? Period. So we could know how fast a wave's going. Or if we know how fast it's going, we know the size of the wave, the wavelength. Now this is most often written in terms of frequency instead of period. So let's change period for frequency. What do? How are those two related? They're inverses. So that is the same thing as the wavelength times the frequency. This is our friend, and it'll help us describe all of these waves. Any wave, not just these. Any wave has these relationships. So when we say, back to electromagnetic waves, different types of light, the difference between infrared light and ultraviolet light is simply they have different periods. Thus, they have different frequencies. Thus, they have different wavelengths. They're different sizes. Infrared vibrates more slowly. We'll review this. Infrared vibrates more slowly than ultraviolet, and it's actually a longer wave. The wavelength's bigger. So you can picture a sine wave more spread out. Big bumps. AM radio. Well, who knows a frequency or a station of AM radio? I think of one off the top of my head, 1080. But its units are kilohertz. That's smaller frequency than 90.1 megahertz. Yeah, megahertz is the units for your FM station. The range there, they vibrate millions of times a second, FM radio. AM radio vibrates in the kilohertz range, thousands of times per second. So the frequency is lower, the period would be higher, and I'll pause.
So is that why you have like music on FM compared to AM because it's better quality because it has a higher frequency?
Is that why you have music on FM as opposed to lots of talk on AM? No. They both have advantages and disadvantages because you can totally have a talk radio on FM and they have music on AM. The quality can be the same. how far they travel and how they interfere. We're going to continue with these other chapters to see what happens to waves. And it's based on their wavelengths and frequencies. And different things can happen. So it'll become clearer, but you could totally do music or talk on either one. So lower frequency, greater period. They're going back and forth. It takes longer. Now, both of these travel at the same velocity, though. I bet you know what speed that is. That's right. It's the speed of light. They're both forms of light, so they both go at the speed of light. So they have the same velocity. So let's look. If they both travel at the same velocity, but one has a smaller frequency, the AM, what does the wavelength have to do? It'll be a bigger wave. And that's true. AM radio sends out bigger waves. The wavelength is larger. You can picture them like this. Where FM radio, the frequency is higher, so the wavelengths are shorter. It looks like this. Was there a comment? In that case, because they're both traveling at the same speed. That's right. Anything that's an electromagnetic wave is traveling at the speed of light. Yes, if this is staying constant, then these would be inversely really proportional. Let's look at sound. If I go la, it's a low frequency. Can you picture the wave? It's got a bigger wavelength, right? It's not vibrating as quickly. La. As opposed to, forgive me, la. It's a higher frequency. So it must be vibrating more quickly. And it is. So the wavelength's shorter. So you can picture waves already. That's because, though, these are both traveling at the speed of sound through air. I didn't change the velocity. How could I change the speed of sound? You can make them travel at different speeds. What's a way to do that? Change the medium. Very good. Remember, a sound is a mechanical wave. It needs a medium. And that vibration traveling through space creates a wave. And if it's going through something that's harder to get through, it'll travel more slowly. Something that's easy to get through, it'll travel more quickly. Again, look at this vibration. I vibrate this up and down. But it sends a wave out that way. And it takes a certain amount of time for this information. I move this. Now it knows. So here's a distance. It took a certain amount of time. Distance divided by time is velocity. We now know how fast the wave moved. That's related to how fast it's vibrating up and down, the time it takes. And these are the relationships that guide that. Yes?
Could you speak to each other in outer space?
Oh, the question. Could you speak to each other in outer space? What do you think? That's right. There's no air, so there's no medium. So I could make a vibration and go, la, and it would stop right here. Because there's nothing to make it vibrate, to propagate that sound to your ears. So all Hollywood, when you hear explosions in space, and pew, 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 wouldn't work.
If, for example, inside, like we were saying, inside the cockpit.
Yeah, inside the cockpit where there is a medium, you could hear stuff. But if the sound, the source of the sound, the vibration started over here, had to go through space to get to you, it can't go through because there's nothing for it to vibrate through. This is sound. Sound needs a medium. Light could travel. You could see the light, but you wouldn't hear anything because it couldn't vibrate through anything to get to you.
So if a tree falls in the forest and no one's
That idea. If a tree falls in the forest and no one is there to hear it, does it make a sound? What do you think? We'll end on that. Sure, it makes a sound. It's just there's no ear to be made vibrating, so you don't hear anything, but there's still a sound, yes. See you Friday.